So I should have been a little bit more forthright before because in some of these examples I have technically been using proportions, and the way that we're going to calculate things using proportions is a little bit different. So please forgive me, but those were really just examples to try to show you how to calculate them using means. So in the last example, technically that was a percentage of income, so I apologize. But I do want to talk about a little bit how this is different, in the sense how we calculate the number of acceptable observations. Again, this is kind of arbitrary. I hope that our n is always bigger because that means our calculations are going to be easier. Again, we can set up a two-tailed or two-sided hypothesis test in the same manner, where maybe we're interested in or think that the underlying proportion in the population may be 0.5. So we set up our null hypothesis that mu is equal to 0.5. Therefore, our alternative would be that they're not equal to each other. Now, I do want to pause for a second and have you think about how would we construct this so that it would be a one-sided test. Once you've actually figured out what the appropriate hypothesis test is and you've got your null ready to go, then you can create your z-score. Now, here you can see we have the estimated or observed proportion in the sample minus what we think that is over the standard error. The main thing is that the calculation here is a little bit different because we're using proportions. But just as from before, this is coming from the sampling distribution of the proportion given that the null were to be true. So in this example, maybe the null is equal to half. But again, notice that we're using mu naught here to calculate the standard error. Regardless of whether or not we're using proportions or means, the way we calculate our p-values does not change. So if we're doing a two-sided test, we're going to look in both of the tails. Last, our conclusion and the way we go about interpreting those p-values is not going to alter at all. So if our p-value is below the critical threshold, we can say that we find evidence that supports the notion we can reject the null hypothesis. And I still highly recommend reporting the test statistic as well as your p-value. As an example, I want to talk about the percentage of self-identified women that are on board positions of Fortune 500 companies in the US. So this is pretty simple in the sense that we know that about roughly 50% of the US population self-identifies as being women, and we want to know, are they descriptively represented in boardrooms? So using data from 2018, we can see that there are about 1,900 female board members. What would be our null hypothesis here? Well, we want to know just whether or not it's equal to 50%. We're not going to go above or below, so our null is just that mu is equal to 0.5. Now, you didn't know this, but the total number of board members in 2018 was 5,670. So our proportion is roughly 1/3. Now, one question that I want you to ask yourself is whether or not the assumptions here are met. And let's walk through this together. So we can certainly say that we have a sufficient number of observations. Then let's proceed in calculating our z-score. we can calculate it such that, and it is again about a third, so a third minus 0.5 over our standard error of mu naught, which is going to be 0.5. And this turns out to be roughly negative 23.57. And again, no one here needs to be a mathematician and memorize any z tables. That is an incredibly large test statistic, regardless of whether or not we're doing a one-sided or a two-sided test. But it's important that we reflect what our research question was, and you'll remember that we are conducting a two-sided test, so we plug that into R, and we get a p-value of basically 0. So we can say that we found sufficient evidence to reject the null hypothesis that women are not descriptively represented in boardrooms in the US, at least in Fortune 500 companies.